Okay, so we've talked about how to create bounds of uncertainty around our estimate of the correlation coefficient, and we are able to conduct a hypothesis test to determine whether or not there is any association between these two variables. Now we want to move on to applying that kind of same framework to regression analysis, and specifically, we want to talk about how to create bounds of uncertainty and do hypothesis testing with regard to our estimators, beta and alpha, and how those relate to the true parameters in the population. So remember from last time that our goal here is that we want to minimize our squared residuals, and our errors, and this is an assumption, are identically and independently distributed in a normal distribution centered at 0 with a variance of sigma squared. In order for us to estimate this regression line, we again want to estimate to this population parameter, the population mean as mu, from whatever data we have, and that is going to be labeled as our outcome y. And remember again, we're trying to minimize the sum of squares, so the distance between what we observe and our expectation of what the mean should be, and that's going to be represented by the mean of our sample. So again, since this least squares function is tracing a conditional mean of a normal distribution, it makes sense to try to minimize that same quadratic loss function. So when we express the sum of squared errors, we can do that using our fitted regression line, which should make sense, right? Like, we want to minimize the distance between what we observe and what our model is going to predict. Now, what I won't harp on, and if you're curious, you can look at the end of the slides. I actually go through the derivation, but what we're going to do is we're going to use some calculus here to differentiate that equation with regard to our two parameters of interest, our y-intercept alpha and our slope beta, and we'll set those derivatives both equal to 0. And again, I'm not going to go through it, but we're going to essentially arrive at two, quote, least squares normal equations. That's basically where we have two equations with two unknowns. So again, I'm kind of jumping through this. I don't want to belabor this point too much, but essentially what we end up finding is that, again, the y-intercept, or where the predicted line goes through with regard to the y-intercept, is going to be equal to the mean of y minus our estimate for beta times the mean of x. And that slope of the fitted line is going to equal the sum of xi over the sum of x squared. And again, there's some kind of fancy notation here that I don't really want to stress too much, where xi is actually a demeaned form. So it's actually xi minus x bar. Now, we won't spend too much time here, but I do kind of want to stress that these are technically the best estimators of the true population parameters that we're interested in. And by best estimators, there are a couple of criteria that we're going to mention, and this is called the Gauss-Markov theorem. And before, I have kind of waved my hands and just saying that these are the most efficient and unbiased estimators, but I haven't really described why. And essentially what we're doing here is, since we're assuming all of the errors are normal, the least squares, and remember, by errors are normal, I mean normally distributed around 0 with a variance of sigma squared. Given that the least squared estimators are efficient among any other unbiased estimator that we wanted to use, not just among linear estimators, which is pretty impressive. And again, I don't want to go into this too much because a bunch of smart people have spent a lot of time doing this, but I'm going to prove this to you again when we go over multiple regression. It'll be the exact same idea. I'm just going to do it then in matrix notation instead of this drawn out y subscript I notation. But it'll be the exact same principle.